Good evening everyone. Welcome to the course Fabrication Techniques for MEMS based sensors from the clinical perspective. This is our live session on week 1 discussion, and I am Rayan Jisma, one of the TAs for this course. I am a research scholar at IIC Bangalore. So first let me introduce myself. As far as my educational background is concerned, I did my bachelor's in electronics and communication engineering, my master's in VLSI and microsystems. Currently, I am pursuing my PhD from IIC Bangalore, and I am working in the field of piezoelectric MEMS resonators for RF applications. My main research interests are piezoelectric MEMS resonators, piezoresistive MEMS accelerometers, capacitive MEMS accelerometers, and so on. We'll be having this live session every week on Monday from 6 p.m. to 8 p.m. where we can discuss any doubts regarding the content that is covered in every week, or we can also solve some problems related to the content. This is a meeting link which we'll be using to join the meeting, and in the YouTube channel I will be uploading the recorded videos, so which you can go through, and in the Google Drive link I'll be uploading the slides that were covered in the discussion session, and you can reach me at this email ID if you have any questions. First we'll start the discussion with a quick recap on the content covered this week. So we learned about various microengineering devices. So one of the devices that we covered is MEMS, so which stands for microelectromechanical systems. So it is basically a system that has both mechanical and electronic components together. So it has both mechanical and electronic components. The size range of MEMS devices can vary between few millimeters to less than a micrometer. So a millimeter is 1/1000 of a meter, and 1 micrometer is 1/million of a meter. So if we consider a human hair, the diameter will be around 100 microns. So MEMS devices will be even smaller than that. So some examples of the MEMS devices are, as we can see in this figure, CMOS image sensors, microbolometer, micro mirrors, and pressure sensors. So CMOS sensors are used for creating images within digital cameras, CCTV cameras, and so on. Microbolometer is used as a detector in a thermal camera. Micro mirrors are used to deflect optical signals, and they also find application in projector displays. So pressure sensor is used to measure the pressure. So here we are having various devices that are used to sense various phenomena. So what are the advantages of MEMS? Why do we need to make devices smaller? So the first one is miniaturization. So since the dimensions of MEMS sensors are in micron scale, the overall system in which the sensor is a part of can also be shrunk. So say if you have a mobile device, you can add many sensors because the size of each sensor is very small. So you will have a very smart device. Then the another advantage is that it has low unit cost. So why do we say that it has low unit cost. So MEMS can be fabricated using a batch fabrication process, means we can fabricate multiple devices in the same step, because in same wafer we can have multiple devices and we can fabricate them together. So when we see the cost per unit of the device, like the cost it takes for fabricating one unit of a device, it reduces drastically. So the third advantage is that the MEMS sensors can be extremely highly sensitive compared to macro scale sensors. So why do they have high sensitivity? This is because these MEMS sensors will have a larger surface to volume ratio compared to macro scale sensors. So this is the reason why they are very sensitive to some phenomenon. Another advantage is that MEMS sensors have very low power consumption. They consume very less power, and many of the MEMS sensors can be fabricated using CMOS compatible process. So along in the fabrication itself, we can integrate MEMS with CMOS circuits. So it provides a platform for readily integration with microelectronics. So most of the MEMS devices have to be integrated with microelectronics to get a system. So next we'll talk about another class of micro-engineered devices called microfluidic systems. So these are systems that manipulate small volume of fluids through small channels with sizes ranging from 10 to 100 micrometer. So we use these microfluidic channels for various applications like cell culture, disease diagnosis, drug delivery systems, drug testing, DNA sequencing, immunotherapy, and so on. So this is just a quick recap of whatever that is covered in the course content. So does anyone have any doubts? Does anyone have any doubts? Okay. So now we can proceed to the problem solving session. So first we'll discuss problem 1. Okay. So the first question is, what role do volatile organic compounds, VOCs for short, play in medical diagnosis? A. They are harmful gases that need to be removed. B. They serve as a fuel source for sensors. C. They can indicate the presence of different diseases. D. They do not influence diagnostics. So what is the answer? So the answer is C. They can indicate the presence of different diseases. So volatile organic compounds, they are compounds that are having very high vapor pressure and low solubility. So at room temperature, they will remain in the gas phase. So some of the common volatile organic compounds are carbon monoxide, carbon dioxide, and so on. So these are these volatile organic compounds are emitted from the human body. So they can act as markers for the health condition of a person. So so they can be used to indicate the presence of different diseases. Okay. So any doubts? Okay. We'll move on to the next question. Problem 2. What is the significant characteristics of VOC concentrations among different individuals? Okay. The first option is A. They are identical among all people. B. Concentration levels are irrelevant to health status. C. VOCs are only present in individuals with specific illnesses. D. Patients exhale different concentrations than healthy individuals. So what is the answer? So the answer is D. Patients exhale different concentrations than healthy individuals. So we saw in the previous question that VOCs are like emitted by people, by every human being, but for a person suffering from certain diseases, the concentration or that they exhale will be different from that of the healthy individuals. So by identifying the concentration of these VOCs, we can determine like whether at what stage of disease they are. Okay. Next we'll move on to the next question. The term IDE in this course stands for. Question. Problem 3. The term IDE in this course stands for A. Integrated Development Electrode, B. Interdigitated Electrode, C. Interdrug Electrode, D. Investigational Device Exemption. So what do you think is the answer? Okay. So answer is B. Interdigitated electrode. So what is IDE? So an IDE looks like this, right? It has so it has two pairs of finger-like electrodes array. So these electrodes are also individual electrodes are also called as digits. So these are arranged in an overlapping fashion. So they are called as interdigitated electrodes. Okay. So then we'll move on to the next question. Problem 4. What is the property of cancer cell measured to characterize breast cancer using piezoresistive cantilever or flexible force sensor? A. Impedance, B. Stiffness, C. Resistance, D. Fluorescence. So what is the property that is measured? So any answers? Yeah. So the answer is B. Stiffness. So what kind of sensor is piezoresistive cantilever or a flexible force sensor? What kind of sensor? So what kind of output does it provide and what kind of input does it measure? Piezoresistive cantilever or a flexible force sensor is mechanical, like it converts a mechanical input into electrical output. That's correct. So among the various options provided, which is the mechanical output? It's the like mechanical input, mechanical term, that is the stiffness. So that is the answer. Okay. Piezoresistive sensing technique is used in MEMS based breast cancer diagnosis using microcantilever. What causes the output to change in a piezoresistor? So option A, change in strain gives change in resistance. Option B, change in displacement gives change in voltage. Option C, change in displacement gives change in resistance. Option D, change in strain gives change in voltage. So here in this figure we see a cantilever that is having a piezo resistor. Okay, so this is the piezoresistor cantilever device that is used to sense the breast cancer. So what is the answer? So everyone, what is the answer for this question? What causes change in the what input causes change in the output of the piezoresistor? What is the output that we measure, and what is the input that is causing the change in the output? Any answers? What are we measuring when having cells suspended in IDE, interdigitated electrodes? So option A is impedance, B is resistance, C is charge, and D is stiffness. So what does how does uh, what happens when we are having cells suspended in IDE? So we know that these are our interdigitated electrodes, right? We have two interdigitated electrodes. Then we are having some sort of analyte in between them. So what we are measuring when we are having this kind of situation? Impedance, right? So if we don't have any analyte in between the two electrodes, what will we measure? We will have infinite resistance, right? We have infinite resistance. Why? Because there is no conductive path between the two electrodes. But when we have some cells suspended in an analyte between the two IDEs, we'll have some sort of conductive path. That conductive path will not just have resistance, it will have some reactance terms as well. So what we measure is impedance, not the resistance. Okay, so any doubts? Move on to next problem. So label the micro machining processes that you see in the following figure. So we see two structures, right? In the first structure, let's say we give it a name A, and the second one let us give a name B. Okay, So which one is bulk micro machining and which one is surface micro machining? Like you can say which is bulk and which is surface micro machining. So here option A is what? Bulk micro machining, and option B is surface micro machining. So why do we call the first one as bulk micro machining? This is because we take a substrate, then we etch out all the regions that we don't want in the substrate and we'll make a device. So that is called bulk micro machining. We start with a bulk material, we etch out and remove all the unwanted material, then we'll make our structure. But in the case of surface micro machining, here what we are seeing is we are having a polysilicon cantilever on a silicon substrate. So we are taking a silicon substrate, we are depositing some sort of sacrificial layer in between them, like this. We are depositing some sort of sacrificial layer here. Then on top of that we'll do polysilicon deposition. Then we will pattern the polysilicon deposition. Then we'll finally etch out this. We'll etch out the oxide that was deposited earlier. So this structure becomes released. So this is a polysilicon cantilever on a silicon substrate. Here we do not like do anything to the substrate, but we will deposit a film and we'll pattern the film. So this is called a surface micro machining. Means we are just doing the micro machining on the surface. Okay. So any doubts? Okay, so we move on to the next question. Problem 8. Surface forces are important in microsystems compared to macro systems because option A, area by volume ratio is smaller in microsystems compared to macro systems. Option B, area by volume ratio is larger in microsystems compared to macro systems. Option C, area by volume ratio is not an important parameter to decide the strength of forces. Option D, none of those. Let's say we are having a structure that is having dimension centimeter. So what we are having is A equal to centimeter into centimeter, that is the area. Then volume V is centimeter cube. If we take the ratio, then A by V will be 1 by centimeter, right? 1 by centimeter is 10 power 2 meter. Okay. If we consider a structure that is having micron scale dimension, then our area will be micrometer the whole squared. So volume will be micrometer the whole cube. Then area divided by volume will be 1 by micrometer. So that is 10 power 6 meter. So if we compare the ratio of the centimeter squared structure and the micrometer squared structure, we can see that the area by volume ratio is much larger in microsystems compared to macro systems. So the correct answer is option B. Okay, so the correct answer is option B. Okay. So is it okay? Next we move on to problem number 9. So while fabricating a sensor that has both microheater and interdigitated electrode IDE, a thin layer of oxide is added between the microheater and IDE. Which among the following purposes does this serve? So option A is avoid electrical shorting between microheater and IDE. B. Ensure uniform distribution of heat generated by the microheater. C. Both A and B. D. Neither A and B. So what is the correct answer? Oxide. So oxide, let's say it's silicon dioxide. Silicon dioxide is an insulator, right? It is both insulator for both heat as well as for electrical. It is an electrical insulator as well as a thermal insulator. So it avoids electrical shorting, but it does not ensure any uniform distribution of heat. Okay, so the correct answer is A. Avoid electrical shorting between microheater and IDE. Yeah. Now let's move on to the next problem. Problem 10. Okay. Which of the following are the characteristics of a good sensor? A. High sensitivity to measured property. B. High sensitivity to all properties. C. Insensitivity to measured property. D. Insensitivity to other application property. E. Both A and D. Sensitivity to the measured property, it should also be insensitive to the other application property, but actual sensor will have some amount of sensitivity to other application property. Like it will not be completely insensitive to other application property. Okay. So next problem number 11. What is the most common shape of commercially available silicon wafers? A. Round. B. Square. C. Triangle. D. Rectangle. So here we can see these are commercial silicon wafers. So they are round in shape, not rectangle, they are round in shape. So they come in various sizes from 2 inch, 4 inch, 6 inch, 8 inch and even 12 inch. So the reason why they are round is because of the way silicon wafers are made. So this we will see in the next week session. So the process involves dipping a seed crystal into molten silicon and then we rotate it slowly as the crystal grows. So we will end up having with a cylindrical ingot. So this cylindrical ingot will be cut into very thin wafers that are round in shape. So like here we can see that this wafer is not exactly round, it is having some sort of cut here, right? So these cuts are called as flats. So the larger cut is called as a primary flat and there will be a smaller cut that is called as a secondary flat. So these are used to identify like what orientation, what kind of doping it is. So depending on angle, what angle is there between the primary flat and the secondary flat, we can tell what kind of wafer it is. So for like each specific type of doping and orientation, there will be a different kind of angle between them. So that you will use to identify the wafer. Any questions? Next, we'll move on to problem 12. The smallest change in input in which a sensor can detect and express as output is called as A. Specificity, B. Resolution, C. Sensitivity, D. None of the above. So what's the answer? So in option A we have specificity, right? Specificity is the ability to assess an exact analyte in a mixture. So like say we are having like we will have sensitivity to only one particular like we will be able to detect that particular analyte even though if it is in a mixture. Okay, resolution is the smallest change that can be detected in the quantity that is being measured. So if we are having a sensor with some kind of like digital output, like say, or any analog output, if we can, the minimum value in the output that we can measure is 1 millivolt, then like whatever input signal that gives us 1 millivolt, that will be our resolution for the sensor. So because that is the like that whatever minimum input that is giving us 1 millivolt will be the value that we can measure. So that is the resolution. So then sensitivity is slope of output versus input. So okay. So now let's move on to next problem. Problem 13. So it was mentioned in lecture that PDMS was used to form microchannels. What processing was used for fabrication? A. Soft lithography, B. E-beam lithography, C. Optical lithography, D. None of the above. Okay, so the answer is soft lithography. So what is soft lithography? So in soft lithography, what we will do is we will first make a mold, then we will put the PDMS on top of the mold. We will cure it and make it hard. Then we'll remove the PDMS from the mold. So then in PDMS we will have whatever patterns that are coming in the mold. Okay, so here in this figure we are having a mold that is made of silicon wafer. So first we have a silicon wafer, we coat a photoresist on it, then we will add a mask on it, then we will remove the mask and dissolve the photoresist. So then we will get a master mask. So then on this master mask we will pour on PDMS, we will cure it and then we will peel it away. So once we peel it away, we'll get a PDMS with the whatever structures that were there in the this one. What were there in the master mask will be there in the PDMS. Okay, so we'll now move on to the next question. Okay. Problem 14. What is the role of heater in the shown figure? So here in figure A we see a heater. Okay, in figure B we see IDT on the top, then we'll have a layer of SiO2, then we'll have a heater below. So what is the role of the heater in this figure? Why do we need a heater here? Increase the temperature of the sensitive material. Why do we need to increase the temperature of the sensitive material? It's because the sensitive material may operate at better at higher temperature, or like whatever properties we measure may be temperature dependent. So depending on like particular temperature range, we'll be able to measure a particular like sensitivity property of whatever we are measuring. Okay, so this is the heater, right? So why does it have this kind of shape? So what is the principle of a heater? Okay, so what is a heater made of? A heater is made up of any metallic, like it is made up of a metal, right? Metal has finite resistivity. So if you want to find the resistance of a length of wire, then we know that there is this formula R equal to rho into L divided by A. So here rho is the resistivity, L is the length of the wire, A is the area of the cross section of the wire, and R is the resistance of the wire. So the heaters work based on Joule's heating effect. So Joule's heating effect is when there is a current that is flowing through the wire, that will produce some amount of thermal energy. So this thermal energy will cause an increase in the temperature of the wire. So like we will tell that heat is produced. Okay, if you are having a wire of resistance R, and let's say I is the current flowing through the wire, then I squared R into T is the amount of heat produced. Okay, so if we want more heat, then what we need is we need a wire with more length, right? So if we want a wire with more length, then what we'll have to do, if we want a wire with more length, then we'll need to occupy more area, right? We need to occupy more area, but in MEMS devices we will not have, like we will not be able to occupy less area, sorry, more area. So that's why like instead of having a very long wire like this, we have folded the wire in such a fashion that it will occupy less area, but it will have large length. So that's why the heater design is like this. Okay, so if we follow the line, it is folded. So this is one of the terminal and this is the other terminal. Okay. So thus we have come to end of our live session of discussion of week 1. So like any questions? So we already saw that like MEMS means micro electromechanical systems, and in the name microfluidics as well, we are dealing with structures that are having size in the micron scale. Okay. And one of the benefits that we see when we go to a smaller scale size is that certain effects gets amplified, so which is beneficial. Certain effects get diminished, which also helps in certain ways. Okay, so if you consider and that's why we will be discussing this topic about scaling laws in miniaturization, where we will see some of the effects of miniaturization for certain scale sizes. So we have something called scaling theory. So scaling theory will tell us what will work when we go to a different scale size and what will not work. if you are seeing what are the different scale sizes, there are like we can categorize them in three main ways. One is astronomical, so which is very large scale. Then we also have the macro scale and the micro scale. So astronomical scale means like planets and those things. Macro scale, any like large scale objects, any machinery, or those things. Micron scale, it's my like we will have both MEMS devices and microfluidic devices as well. So one thing that we see is that like some of the effects or forces or like certain physical quantities which are effective at one of the scale sizes will become insignificant at other scale sizes. For example, if we consider the gravitational forces, the effect diminishes as the scale size decreases. Okay. So they are dominating when we are seeing at the astronomical scale, but not at macro scale or in micro scale. Then, if we are considering macro scale motors, there we use magnetic forces for actuation. But if we consider, we do not see any like micro scale motors where we use magnetic forces for actuation. Instead, we use electrostatic forces for actuation. So why do we do this? This we will see shortly. If we are considering the types of scaling laws, so like we can say that like how we scale an object or a property will depend on two important things. One is the physical size of the object, and the second thing is it will depend on size and material properties of the object. So first we will look at the scaling in geometry. Okay. So in geometry, we have two important physical quantities. One is surface, you can say it as surface area or surface, and the other is volume. So volume, this is related to mass and weight of the object. Again, this is again related to both mechanical and thermal inertial. So thermal inertial is related to the heat capacity of the solid, and the heat capacity of a solid is a measure of how fast we can heat or cool a solid. Okay. The surface area is generally important when we are talking about pressure or any buoyant forces in fluid mechanics. It also plays a role in thermal domain when we talk about heat absorption or dissipation by a solid when we are having the convective heat transfer. So surface to volume ratio is an important parameter. So we know surface is proportional to length scale squared and volume is proportional to length scale Q. So your surface volume ratio is proportional to length scale, is inversely proportional to length 1 by n. So as the size decreases, the surface to volume ratio increases.
So next we will look at scaling in dynamic forces. So we know that displacement is velocity naught into t plus half into at squared. If we consider the velocity at time 0, 0, then we will have displacement v naught equal to 0, which means displacement equal to half into at squared. From this, we can get a as 2 into s into divided by t squared. We know force is mass into acceleration. So mass into 2 into s divided by t square. Hmm. So as we decrease the size, there are two important things which will change. One is the mass, and there is also a chance that the displacement s will also change. So as we decrease the size, mass decreases, and the displacement, it depends on what kind of effects we are like placing, we are talking about. So however, in like if we assume that the displacement is also decreasing as the mass decreases, then we can see here that the force as the size of the object size decreases, the dynamic forces also decrease. So this is the effect of scaling in dynamic forces. Next, we will look at scaling in electrostatic force. So if you are having two parallel plates like this, W is the width of the plate, L is the length of the plate. Then the electrostatic energy or the electrostatic potential energy induced in the parallel plate is given by U equal to half into CV square. So here C is capacitance, which is given by epsilon naught epsilon r A divided by D. So A area is width into length divided by D. So here D is the gap between the plates. Into V square. So V is the breakdown voltage, or it is the voltage that is used to that is required to initiate the discharge. Yeah, if you consider like the variation of breakdown voltage with the gap, then we will have a plot something like this. This curve is called as Bastian curve. Okay, so this curve looks something like this. So it has different dependence at different length scales. Here, this is 5 micrometer and this is 10 micrometer. So if the size is greater than 10 micrometer, then we can say that it has a cubic dependence. So for D greater than 10 micrometer, B is proportional to length cube. As we saw in our earlier slide, epsilon naught, epsilon r, width into length divided by D into V squared. So here, these terms do not have any length dependence. This term, width, length, distance, V squared. So these are the three terms that have a dependence with the dimension. So we have length dependence, again length dependence, L cube the whole square divided by L. Okay. I think it's around L power 7. Sorry. For a great size greater than 10 micrometer, voltage is having linear dependence. So here you will have L power 4, which you will get L cube. So as size decreases in linear dimension by 10, the electrostatic force will decrease by 1000. So if we look at the electrostatic force, okay, this is electrostatic potential energy. Electrostatic force is dou U divided by dou D. So for this, if you are seeing, you will get your electrostatic force, which is proportional to length scale square. So if you are reducing size by 10 times, electrostatic force decreases by 100 times. So as we move on to micron scale, the electrostatic force decreases. However, it does not decrease very drastically. Okay. Next, we will see the scaling in electromagnetic forces. Okay. So electromagnetic forces, they can be induced in a conductor when there is like we are having a conducting loop where current is flowing through it, and we are placing that conducting loop in a magnetic field B. So the what happens is the electromotive force will drive the electrons through the conductor. In the case of electromagnetic forces, if we are decreasing the size by like 10 times, then the electromagnetic force will decrease by 10,000 times. So here electromagnetic force scales with length power 5. Okay. However, like we saw earlier, the electrostatic force scales with length scale squared. So when we compare these two, like uh, if we are trying to use electromagnetic force for actuation, or when we are trying to use electrostatic force for actuation, like in micron scale, we'll see that electrostatic force has a better effect, right, compared to electromagnetic force, because it diminishes very less in micron scale. So that's why like generally any actuator kind of devices, like you'll see them having like electrostatic force as actuation instead of electromagnetic force. Now we'll look at scaling in terms of electrical parameters. Okay. So like resistance is an important term that we see. So resistance R, it's denoted by R. It is rho into L divided by A. So rho does not have any length dependence. L has length dependence in one scale, and area has length dependence in two. So 1 by L. So like as the size decreases, the resistance increases by one. Like size decreases by 10 times, resistance increases by 10 times. Then we have applied voltage V. That does not have any dependence in the length scale. Electric field energy density. U, it is given by half into epsilon into E squared. So this has like mine uh hmm, same as a resistance kind of dependency. Sorry. This has 1 by squared dependency with the length scale. If you look at dielectric permittivity, it does not scale with dimension. Electric field, E is given by V by D. So it scales inversely with length. Okay. So like if you are considering available power, the energy available is proportional to L cube. If we divide power divided by energy average, then what we will get is we will get the proportionality L power minus 2. So as like the size decreases, we will have like greater power loss as the resistance increases with the decrease in size. So this is one of the disadvantages of scaling down in the power system. So these are some of the examples. Like that, we can also find scaling laws related in fluid mechanics, heat transfer, and so on, which are some of the domains which are used in like micron scale devices. Okay. So when we design, like say when we make a micron scale device for a particular application, we have to consider the scaling effects. Like say if you want to make a motor, then you would prefer using electrostatic force for actuating the motor instead of electromagnetic force, because you see that the electromagnetic force it is very insignificant at micron scale when compared to like higher scale objects. Thank you.